Chapters 9 and 10 form one continuous inquiry. We begin with a simple question. How do we learn from nature? And then we ask the next question. Once we have learned to observe, reason, and test, what is the nature of locomotion itself? Science begins with phenomena. A falling body, a swinging pendulum, a rising tide, a planetary orbit, or the scattering of light is something nature actually does. The phenomenon comes before our explanation of it. The central principle is simple. Reality first, explanation second. A phenomenon must not be confused with an experiment. A phenomenon occurs whether or not we design a test. An experiment is a test designed by us to reveal or examine what nature does. Experiments are therefore valuable, but they must remain faithful to the phenomenon. If an experiment is designed only to prove an expectation, there is a danger that we begin seeing the theory rather than nature. For this inquiry, the phenomenon remains the starting point. Why do we observe physical phenomena? Not merely because they are interesting, but because they point toward causes and variables. The swing of a pendulum, the path of a projectile, and the orbit of a planet each reveal something about the conditions producing the observed motion. One event rarely reveals an entire law. We learn by comparing events, recognizing consistencies and differences, and connecting many observations into a pattern. Observation is therefore the gateway to causal understanding. Observation alone does not secure knowledge. The mind must connect observations through reasoning. Observation supplies the evidence. Reasoning reveals the order. If we reason without observation, our reasoning can become ungrounded. If we observe without reasoning, the observations remain disconnected. The manuscript therefore places observation and reasoning together. Nature gives us the evidence, and disciplined reasoning asks what follows from it. The manuscript proposes a rightful sequence for scientific understanding. First, observe phenomena as they appear in nature. Second, analyze consistencies and differences. Third, design experiments to test those consistencies. Fourth, formulate principles and laws from repeated verification. Fifth, translate them into mathematical form for clarity and communication. And finally, return again to phenomena to test and confirm. The important point is the direction of the sequence. Mathematics and models should help us describe nature, not dictate what nature must be. From particular events we begin to search for universal principles. Every physical event is a particular expression of underlying variables acting under definite conditions. The conditions may change, while the variables we are investigating remain the same. A falling body, a pendulum, a projectile, or a planetary orbit may look very different. Yet the task of physics is to distinguish what belongs to the universal variable from what belongs to the particular conditions. This distinction helps us look for unity behind diversity. At this point the inquiry turns naturally toward locomotion. If phenomena are our starting point, and if motion appears throughout the observable universe, then motion itself becomes a central phenomenon to investigate. The manuscript distinguishes physical, uncontrolled motion from motion that depends upon continuous artificial or biological control. The question is no longer simply, what moves? It becomes, what is locomotion, how does it begin, and what keeps its effects visible after the initiating cause has ended? Chapter 10 begins with a strong proposition. Physical motion is not to be treated merely as an unexplained property of matter. The inquiry asks where motion comes from. A push, a release, an impact, an ejection, or another physical event can provide an initiating cause. Once motion has been acquired, the body can continue along its path under the conditions acting upon it. Thus the manuscript shifts attention from motion as something simply present to motion as something that has a history and a cause. The manuscript proposes pressure impulse as the initiating cause of locomotion. Impulse is force delivered over a finite interval of time. A hand can push a stone. A hammer can strike an object. A large physical event can eject matter. In the proposed framework, such an impulse gives matter its initial velocity and momentum. Once the initiating force has ended, the acquired motion can continue. This leads to a causal sequence: an initiating impulse, acquired momentum, and then the forces or resistances that shape the subsequent path. This framework is then applied to orbital motion. An orbit is described as a balance between acquired horizontal momentum and central gravitational pull. Without the acquired horizontal component, the body would move inward. Without gravity, it would not remain bound to the central body. The important distinction in this chapter is between initiating motion and restraining or modifying motion. In the manuscript's language, impulse drives, momentum carries, and gravity tames. The same reasoning is extended from familiar terrestrial examples toward celestial motion. Mass ejections, collisions, and other energetic events are proposed as possible sources of pressure impulse in cosmic systems. The central question remains causal. If a body is moving, what event gave it that motion? The manuscript therefore treats locomotion as acquired rather than inborn, and places the origin of motion before the later study of how that motion is shaped. This gives us the central chain of the two chapters. We begin with phenomena. We observe them. We analyze consistencies and differences. We reason about causes. We test. We formulate principles. We express them mathematically only after the physical pattern has been established. Then, when we turn to locomotion, the causal chain becomes: impulse begins, momentum carries, and gravity or resistance restrains. The purpose is not to replace one slogan with another, but to make the questions of physics more precise. The deepest lesson of these two chapters is methodological. Nature is the starting point. Phenomena are the evidence. Observation identifies what happens. Reasoning connects events and searches for causes. Experiment tests the consistency. Mathematical language can then express the resulting relationships with precision. And when the subject becomes locomotion, we must ask not only how an object moves, but how that motion began, what it carries forward, and what changes its path. The next chapters will examine these questions more closely, beginning with gravity and its proposed role in motion. Chapters 9 and 10 therefore form a natural bridge in the book. Chapter 9 establishes how we should approach nature: observe phenomena, reason from them, test carefully, and return to reality. Chapter 10 takes that method into one of the deepest physical questions: locomotion. The inquiry now has a direction. We have phenomena before us, variables to distinguish, causes to investigate, and motion to understand. The work continues by following nature rather than opinion.